Please join me in welcoming to the Distinctive Voices podium, Dr. Erik Linstead.
Thank you. Hello. And the technology works, which as a computer scientist is just amazing. It never works out that way. Great, we're off to a good start. So I am Erik Linstead. I am an assistant professor at Chapman University, where I spend most of my day looking at data and teaching talented undergrads and grad students. So it's a really good gig. Before I was a full-time academic, I spent 12 years at Boeing as a software engineer doing all sorts of cool systems programming. So really enjoyed that. I think I've managed to sort of totally hit it right with my life so far and have some great industry experience, and now being a professor, which is pretty much about the sweetest job imaginable. So a lot of fun. These days, I get to spend my time in the machine learning and assistive technology lab. And MLAT, was really designed because I enjoy data. I think data is really cool, and part of that stems from a long-standing interest in human intelligence and artificial intelligence, and thinking about how the brain works and how we can use hints from biology to do cool stuff in silicon. So I really wanted to be able to have a lab where I could focus on artificial intelligence and machine learning, and had actually thought about doing that for a long time when I was at Stanford and I was focusing on database systems. I happened to take an artificial intelligence course that gave me my first sneak peek at machine learning, and I said, well, okay, this is about the coolest stuff ever, and this is what I want to do. Finally, when I moved to Chapman on the tenure track full time, we decided to build this lab and try and do some good. And I should tell you that one of the quotes that's on my office wall is from Richard Feynman, and it basically says that no problem is too small or too trivial if you can actually do something about it. And that was sort of the motivation for my lab. I thought, well, there's lots of really great stuff that we can do with computing. There's lots of problems that we need to be solved. So let's just focus on tackling meaningful problems, and hopefully if we can do something about them, then it'll all have been worthwhile. And for the most part, it has. My lab is, I guess to use a term that my dean likes to use to describe my work, it's the dog's breakfast, right? It's pretty much an eclectic mix of whatever we feel like working on. And so we do some really cool stuff in bioinformatics, looking at things at the cellular level, or neural networks, or mobile applications for assistive technologies. And now we're even starting to get into virtual and augmented reality because it's getting affordable enough and robust enough to actually be scalable for a lot of applications. So we're having some fun with that. But I think at the end of the day, pretty much everything we do gets back to the data. And I mean, after all, right now, that's what everyone wants to talk about. Big data, that's what the hype is all about. And I think that's really exciting. One of the reasons it's exciting is because I feel like I have job security like I've never had job security before. It doesn't seem to matter what line of work you're in. Everyone has too much data, and they want someone to do something interesting with it, right? And I'm your guy. And that's wonderful. But I also understand that one of the reasons there's so much hype surrounding big data isn't just because there's folks going off working on interesting machine learning algorithms. This is also the result of infrastructure like the internet, where it makes it so easy to connect folks and share large volumes of data and collect large volumes of data. And we all walk around with, by let's say space shuttle standards, a supercomputer in our pocket, and we're constantly connected. And I think for me, when I'm thinking about the types of problems I want to work on in MLAT, well, if I can look on Facebook in the morning and know what everyone is eating for breakfast and what your favorite aftershave is, then I ought to be able to use that level of knowledge to solve some really important problems as well. Not that I don't appreciate a good aftershave suggestion. I think that it's a great time to be working with data. Note that I don't say it's a great time to be a data scientist or a data analyst. I mean, that's wonderful if you want to be, but I think it's a great time just to be a mathematician or a statistician or a biologist or a chemist or a psychologist, right? Because I think as a result of being able to share all this data, all these endeavors that maybe 10, 15 years ago weren't thought as really being data-driven, now they're data-driven. And everyone has too much data. You need to look at that data to do smart stuff, and it requires a lot of talented people from a lot of different areas. So to me, the really great thing about big data isn't just big data because it's sexy and there's a lot of hype surrounding it. To me, the really great thing about big data is it promotes interdisciplinarity and gets a lot of really great people with different backgrounds talking about solving a common problem, and then really cool stuff happens. And so my talk tonight will sort of be talking about some of that, some of the work that we do in my lab, talking about sort of my progression as a machine learning researcher from some early not so flattering impressions about data science, and now to the type of things that we do now, which admittedly, some of them are small data types of problems, but they're still meaningful problems. So that's sort of the goal. I gotta say, when I first started studying as a computer scientist, as a new college student, as an 18-year-old, and I started to hear about this thing called data mining, I was not at all impressed. This wasn't something that I wanted to do. And by and large, it's because some of the first examples I saw of this thing called data mining or machine learning were basically something that I had seen in high school chemistry and biology classes, right? It's, oh, collect a bunch of data points and then draw the line that best describes the trend. Simple linear regression. And you can estimate the regression parameters pretty simply using nice math. It's beautiful math, but I mean, certainly, nothing that I thought was absolutely amazing or something that you really needed to throw a computer at to do cool stuff. And so I kind of decided that, look, if this is what the machine learning part of computer science is about, that's not really what I want to do. I want to work on big data, large volumes of data. That's where the hard problem is. And so I focused on database systems, thinking that the storage was really the hard part and the analysis wasn't really so interesting. And obviously over time that's changed, and it's changed a great deal. And I think a big part of that is just because, thanks to Moore's Law and other things, now we have computational resources available to deal with big data that we just didn't have before. And so now we can start thinking about modeling large volumes of data, not just theoretically, how do we go about it, but we can actually do it because we can throw things like GPUs at large image data sets, and we can get those data sets, and they're publicly available, and we can aggregate them really easily. And we have all sorts of clever algorithms now to combat overfitting and make sure that the models that we're building are generalizing. But at the time, this wasn't really there. There wasn't any Amazon Web Services where if I had a huge data set that I couldn't fit in memory on my machine, that I would just go off to the cloud and that would take care of it for me for pennies, right? So because I didn't really think that I'd ever have a chance to do a lot of hands-on stuff, I shied away and focused more on the storage. And that all changed in 2005 when I met Pierre Baldi. He's a professor here at University of California, Irvine. He's a chancellor's professor in machine learning. And I was thinking that I was going to go back and do my PhD in database systems. And I met Pierre, and he said, well, you don't want to do database systems. That's boring. You want to do machine learning. And I said, yeah, I've seen machine learning, right? You can't really do real machine learning. The computational resources aren't there. And I don't want to do theoretical stuff. I really want to do applied cool stuff. I want to build systems. And he said, well, I think you're wrong. And the example he gave was, how many stars are there in the universe? And I didn't know. And he said, well, about 10 to the 22. And I said, okay, well, that's a pretty large data set, right? I'm listening. And he said, okay, well, what do you know about molecules? And I said, well, whatever I forgot in 11th grade chemistry. And he said, well, okay, well, there's about 10 to the 7th existing small molecules, give or take. And he said, well, what do you think about virtual chemical space? And I said, I have no idea what you're talking about. He said, okay, well, let's not just talk about molecules that are in existence, but let's think about every possible small molecule that could actually be synthesized, right? Let's talk about doing that, so a virtual space. And then let's think about being able to predict properties about those molecules in a way that we can rethink how we do drug discovery and cancer research and something like that. And I said, well, that's really cool, but there's no way that's a tractable problem if you're talking about 10 to the 60. And he said, well, you're wrong, and I think we can get there, right? And so I really sort of appreciated his enthusiasm and just this sort of acknowledgement like, yeah, we can do machine learning on data mining on these just massive data sets. And not only can we come up with some cool theoretical algorithms to do this stuff, we can actually apply it and do useful things like try and develop the next affordable cancer drug. And so I said, okay, you're right, I want to do machine learning, I don't want to do databases anymore. And it was a huge victory. So having signed on to Pierre's lab, the first thing that he put me on was a database project. He has a great sense of humor. But it was a cool database project. It was called ChemDB. And basically the idea was that it was an online, searchable database of small molecules. And we would use machine learning to predict things like solubility and toxicity and be able to do rapid search. And not me, because I, at the time, certainly didn't have the background to do it. But we had other students in the lab that were working on things like you come up, let's say, with a cancer drug, and it has really horrible side effects, or it's prohibitively expensive, and you need to come up with an alternative. Well, how can we find other potential molecules that are structurally similar and therefore hopefully functionally similar, and then try and create them for less money, or so they don't have such horrible side effects. And so some folks were making progress on that while I was helping with some of the database backend and some of the text search. And it was incredibly gratifying to be working on something like that, because not only was this absolutely huge database that we got to work on, aggregating all the data and sorting through it and trying to come up with clever search mechanisms so you could get the results you needed in less than a year, something like that. But there was actually this potential that maybe we could change day-to-day lives, and that was really cool. And even as a 25-year-old, I started to think, well, this is really, if I ever find myself in a situation where I'm doing research for my job, this is the type of research that I want to do. And so I owe a lot to Pierre to sort of opening my eyes to that. But like I said, I wasn't a chemist, I was a software engineer, and had worked at a lot of different software projects at Boeing and looked at a lot of source code. And so talking with Pierre and some collaborators, we thought, well, software and molecules kind of sort of aren't all that different. I mean, the vocabulary is different, but there are structural properties, and those properties are useful for predicting things about molecules, predicting things about code. And so we came up with this really grand plan that we were going to use machine learning and information retrieval to go out and look at all the publicly available source code that was on the internet, or at least as much as we could get until the hosting provider shut us down for scraping their websites. And we would try and they did, but we would try and do that and analyze the code and see if we could kind of understand what happens to software when it's being developed in the wild. What types of software are people developing? How good is it? How evolvable is it? How maintainable is it? What are the developers' expertise, right? And sort of the idea here was not just doing it to do it, but when you look at open source software, there's this huge promise of reuse, right? We don't want to reinvent the wheel. That costs time and money. So if there's good stuff out there, we should be able to find what exists and then be able to bring it into our own projects, software, licensing notwithstanding. So it seemed like a really interesting avenue for doing what at the time was this thing that people were calling empirical software engineering, and it was sort of a new field. But no one was really doing, I don't know, I guess, I'll say hardcore machine learning, but that's not really being kind to the folks that were doing some really great research. But I wanted to apply statistical machine learning in this area. So we did, and we built a data set that consisted of about 38 million lines of source code and 12,000 open source projects from about 9,000 software developers. So at the time, it was pretty much one of the largest databases that you could get on open source software. And we built a pretty massive architecture to go along with it. Now, again, this is funny because this is all pre-Amazon Web Services and the cloud, right? So we had to completely roll our own for everything. And if you were to do it again today, you could do it with much, much less effort and with much less capital expenditures. And this is also when I learned another very valuable lesson about doing academic research. It makes a big difference if your PI has funding to buy hardware. And that's been valuable at various points in my career. And so we built this platform called Sorcerer that would go off and crawl things like Apache and SourceForge and download code and all that good stuff. And we would mine it and we would index it and we'd try and make it so you could search it and find things that you were looking for really easily. And just like we did with ChemDB and chemical space, we looked at the structure of software and we tried to use that as a hint about what it was doing and how good it was, and if an implementation seemed really robust, or if it didn't seem like it was, or if it seemed like it was brittle. And it was a great experience. Something really interesting happened as part of this project. I had sort of mentally always understood that machine learning, data mining algorithms were supposed to be agnostic about the type of data that they were getting, right? And so it didn't really matter if you're looking at DNA with A's and C's and T's and G's, or binary with zeros and ones, or software or whatever. The algorithm should be robust to that. But I didn't really think about the fact that a lot of the reasons the algorithms work so well is because there are some inherent underlying structural issues that seem to hold across all sorts of data. And one of the things that we saw early on was that we could come up when we were looking at the vocabulary of software and the way people named their identifiers and whatnot, we'd come up with all these power law distributions. And power laws show up all over the natural language processing literature. And it was interesting because this thing that I thought really was so different from other types of data and what had been done, it wasn't all that different. Yeah, the vocabulary was different, but a lot of the same ideas still held true. And this was important for a couple of reasons. One, it seemed like there would actually be algorithms available so I could finish my PhD in less than 5 years, which was the cutoff my wife gave me before she said she would file for divorce. So that was really useful. It helped. And the other thing was it really made me understand that a big part of doing machine learning is just actually having the domain expertise in the room so that when you look at data, you can understand what's going on and the nuances of it, right? It's not enough just to be really well versed in all the algorithms that are out there and all the computational techniques. I mean, definitely helps, it's important, but you need to know more. You have to have that insight into the data that you're looking into. And I think that gets back to the notion of interdisciplinarity and why that's the real beauty of big data research, because it's work that has to be inherently collaborative if you want to be successful, at least in most cases. So we had found this cool structure and we said, well, okay, well, if software seems to look a lot like the types of stuff that we see in natural language, then maybe we can apply some text mining techniques to kind of let the computer figure out what software was doing and what the people that were writing it were good at and all that good stuff. And in 2003, a paper had come out by David Bly, Andrew Ng, and Mike Jordan, and they had come up with this algorithm called latent Dirichlet allocation, which sounds really sexy because it is, but mostly it just assumes a probabilistic model with text, and it assumes a generative process where if you were to look at a document, that document was basically generated by taking a die that had a whole bunch of topics, and you'd one at a time throw that topic die and you get a topic, and then you would sample a word from the topic with another die. And so mathematically, statistically, it was very pretty. And at the time, it was being used all over the place in research to in an unsupervised way, without human intervention, discover patterns in text in all sorts of cool areas like news or historical documents, conference abstracts, Some folks were doing some work looking at NSF grant proposals and trying to be able to do some inference on those. So it was really sort of cool, and no one had applied it to software before, and it seemed like a good way to start. And once you sort of convince yourself that, well, software is really no different than anything else, than any other data, it just has its own syntax and its own vocabulary that you have to deal with, then you can kind of start doing cool stuff. And so here's an example of running an algorithm, running latent Dirichlet allocation on this 38 million lines of source code and the types of topics that it comes up with. Now, the topic on the left, the high-level topic, this is something that a human did to describe the topic on the right, which is what the computer came up with. But the important thing is the topic on the right was come up with in a completely in an unsupervised manner. A human being did not have to tell the computer, this is what software concepts are about, or these are the types of things that programmers do. The computer figured it out on its own. So that first topic where you see SQL, database, update, JDBC connection, the computer figured out that there was this notion of database programming, and the way that that was done in Java was with a JDBC through connections to the database. Or the second one, file path, dir directory, file name, a file processing topic, or server, client, host address, port, network programming. And we could see the computer sort of very accurately picking up these high-level concepts that described software engineering, the aspects of software engineering, if you will. And this was really fascinating. And so we wrote our first papers on doing statistical topic modeling on source code. And then good things happened. From there, we realized that once you could figure out what topics were in source code, you could also understand how they sort of came and went. And you could understand evolution of a software code base, such as the introduction of a piece of functionality where all of a sudden between version 2.1 and version 3.0 of Eclipse, you see this jump here. And this is when a feature was integrated. Or here, for Argo UML, you see this huge dip between version 0.12 and 0.14, where they did a refactoring that decided something wasn't working well, and so they ripped it all out. And you can see the algorithm picks up on that because the topic becomes less prevalent. And some stuff like just plain vanilla string processing, append, reserved, buffer, string, that just is relatively linear because the more code you add over time, it sort of grows proportionally. Additionally, we found that we could look at the topics that different software developers wrote about, and we could use that to cluster them. And this is called a multidimensional scaling. Doesn't really matter what the X and Y mean. They don't mean anything. It's just the boxes that are close together are more similar. And this proved to be really useful for something that is called triage in the software engineering world, where a problem goes wrong, and if something goes wrong in a piece of code, you need to find someone that can fix it. And if you have a lot of attrition and perhaps one developer is left, you need to find someone with similar skill sets and similar expertise to fix the bug. And so we were able to propose using statistical topic modeling to do just that and model developer expertise. And again, the important thing here is we didn't have to know anything about these software developers other than what were the source files that they worked on, which we could get really easily using the code versioning systems that were available online. In fact, in 2007, we wrote this up and we submitted it to a conference where they had a challenge. It was basically find interesting patterns in the Eclipse code base. And we submitted this, and they were quite certain that we must have been talking to folks that were working on the Eclipse project. And it was, no, the algorithm just works that well. And to me, it was really amazing because it didn't require a complete overhaul, right? I mean, because structurally there are enough similarities between software and other languages, it just sort of worked beautifully. And that was probably one of the things that really hooked me on being a machine learning scientist after that. This thought that there was this kind of, I don't know, even though the data could be noisy and messy and weird looking and you needed someone to interpret it for you in some cases because it just wasn't your area, if you could get the right folks in the room, there's just all this cool mathematical and computational machinery that you could throw at it to do cool stuff. We built a search engine, a software search engine, where you could search for code and then download it, and that way you could reuse it in your project. So for those of you who have a background in software engineering or computer science. I don't know about you. I can do bubble sort and insertion sort pretty easily off the top of my head. If you ask me quick sort, I'll probably need a little while. Have to go to church and light some candles and hope for the best. The point is, using something like this, you don't have to reinvent the wheel and code from scratch. You can just go and find the example you're looking for and then use it, and then also understand structurally what's going on in the code. So, for example, in this fingerprint detail, you can see things like, well, how many nested for loops are in this piece of code? And if someone gives you an implementation of quicksort with 10 nested for loops, you kind of go, I don't think you really got that right. So finished my PhD, having done a lot of really cool stuff in empirical software engineering and software mining, and it was great, but I was about done with software, right? Just didn't really want to do that anymore. I wanted to find something else. And it happened several years later where I was teaching at Chapman, and I had a master's student. She came to me and she goes, I have an idea for doing some text mining. And I said, I will do text mining with you, but it cannot be on software. Can't do that anymore. And she said, okay, well, we're going to do it on insurance billing statements and emergency room medical records, and we're going to see if we can predict the ICD-9 codes, the diagnostic codes that are used to talk about things. And I said, well, that sounds really cool, and it's definitely not software, so let's do it. So again, it was the same story. We took the data, which was now something that did not look at all like source code, and we processed it, and we got the text out of it, and we modeled it, and we passed it through some text mining techniques, and sure enough, it worked, right? And so we could see topics like lung, pulmonary, probably mass, yearly, couple consistent, and so on and so forth. And got topics out where even though the data was completely different than the data we had used before, a lot of the structure was there, and we could see cool patterns. And this was sort of neat because it reminded me of my early days on ChemDB and sort of coming back to something that could really be impactful. And I thought, well, maybe I should do more medical informatics because it seems like that can be something I can feel good about. A couple of years later, my daughter had been diagnosed with autism. I was feeling really frustrated because I couldn't get her caregiver team to sort of communicate. Really, I was frustrated with myself because for someone who sort of prides themselves on being a type A type of scientist, detail-oriented, I go and talk to her neurologist, and they would say, how old was she when she said her first word? And I'd give an answer. And then when they asked me again another time, or I talked to another one of her specialists, that answer would change, like plus or minus like 2 months, right? How ridiculous is that? One, I'm having to repeat the same thing over and over, and even I can't get it right. And so doing what any professor would do when they have all sorts of undergraduates who are looking to work for free for experience, I gathered a few of them together, and I said, we're going to build this platform called AMP, the Autism Management Platform, and we're going to come up with a convenient way for caregivers to share data for a particular child, and we're going to have ways to do analytics. So that way, when the pediatrician or the neurologist changes a medication and they want to know, well, did that lead to better behavior at school or worse behavior at school, now we actually have quantitative data that shows what happened or nothing happened, and that seemed like a win. And so we built AMP, and it was really great. It started to get my head wrapped around some of the issues that happen when you want to use big data and machine learning in medical informatics. And admittedly, even though it was a really cool platform, it never achieved much success. And a big part of that was just this fear of folks interacting with medical data and what about HIPAA and all these things. And so before when we'd go and talk to people and tell them about this thing that we had built, before the words came out of our mouth, they were almost already saying no because it involved them sharing data that maybe would get them in trouble. But that was okay because the lessons that I learned personally from building AMP and going through that experience have really shaped the way now that I do all the other clinical research in my lab. And plus, it was just pretty cool to build something and work with that group of guys. They're really awesome. And the other thing that happened is in the process of building AMP, I got hooked up with some folks at the Center for Autism and Related Disorders, Dennis Dixon and Doreen Granpeesheh. Doreen's the founder. And she basically came talk to me, and she said, I understand that you have a daughter on the spectrum, and that's, this is sort of a personal mission for you, and you want to do something about it. And I said, yeah, I want to do something about it. And she's like, okay, well, I'm going to introduce you to Dennis, one of my, basically my chief analyst, and you guys can talk. And one of the things that I told Dennis was, as much as I like being a computer scientist, the only time I really felt that I made a bad decision was when my daughter was diagnosed, because I thought, well, if I had been an MD or a neurologist or a psychologist, maybe I could do something really helpful for her, and instead, I'm a computer scientist. And he said, well, that's actually really good for us because we have a ton of data and we don't know what to do with it. And I said, I'm your guy. So we started working and worked on a few things, and one of them was this high-dimensional cluster model of the autism spectrum, which basically showed that despite the fact that autism is a spectrum, and if you've seen one kid with autism, you've seen one kid with autism, we do actually see these behavioral phenotypes. And right now we're looking at taking these behavioral phenotypes that we've extracted using machine learning, and we're trying to understand the treatment paths that have the greatest efficacy for each of those phenotypes. So that way, day one, a child gets diagnosed, they come into clinic, and they have a treatment path that's personalized for them to the best of our ability. And you can make sure that if your insurance has funded X hours of therapy, then every one of those X hours is being used to the best extent possible. I also managed to meet some really cool folks at UCLA, Connie Kasari in her lab, and along with my couple of undergrads, we decided that we would look at building an affordable AAC device, augmentative and alternative communication. So there are some popular AAC devices where you basically speak by pushing pictures on a tablet, and it says the word for you, but they're incredibly cost prohibitive, several $100s for the software itself, plus they only run some of them on iPads, which cost several more $100s. And again, in a day and age where you can see what I had for breakfast and I can see what your favorite aftershave is, I don't think we should be putting folks in the position where they have to spend $800 to $1,000 to get AAC in the hands of kids who need it. And so we've been working on an affordable alternative that you can use on commodity tablets. Our goal is to be able to deploy this for less than $100 and hopefully much less than that for folks who need it. And once it's ready, the idea is that we're probably just going to open source it and put it out there for the community to develop with and do their own thing. I want it to be sustainable. So that's been good. Something weird happened lately. Some of my students came to me and they said, we should do a software mining project. And I said, okay, because I don't know what I was thinking. But in the meantime, I had learned some cool things looking at clinical data, in particular temporal trends in clinical data, things that are happening over time. And so I looked, and sure enough, there wasn't really a lot of time series analysis going on in mining software repositories. And so my students, Abby and Christina and Natalie and Elizabeth, they worked on some stuff, and we found that indeed you can, if you have continuous integration data from software, you can find temporal trends. And in fact, we could find interesting trends about developers' daily habits and weekly habits and when they like to work and when they like to take a day off and when they like to commit their code and when they like to not commit their code for a while. And that was fun. It was like going back to something that I'd been away from a while, so it was a good homecoming. And we've been doing some more of this, and I'll show you in just a sec. Well, like I said, everyone has too much data. So after we were starting to make some success in all these other areas, my student Cody Arbuckle teamed up with a pharmacist in Chapman School of Pharmacy, Dan Tomaszewski, and he said, I have a whole lot of data on prescription medication, and we're really keen to find out if people are adherent to their medication, if they actually take it when they should, and what are the factors that maybe predict non-adherence. And so we mined the data, and one of the things that we found is thanks to the internet, which in so many ways allows us to do this type of research, a lot of folks, especially young folks, are really struggling with health literacy and understanding what sources are worth listening to when it comes to medication and what sources are probably best ignored. And so, we found the fact that if you were young and you really relied on the internet to get information about your medication, you tended to be far more non-compliant That was interesting. And so now we're in the process of writing this up. And the real message here is that if you care about changing day-to-day lives, then we need to think about what it means to promote health literacy to the younger generations in a way that's not sort of the same typical ninth grade health class that we've always had, right? Where, try not to eat too many fatty hamburgers and don't get an STD in high school, right? We can do better than that. We were approached by a cardiologist in conjunction with Hisham El-Askari, who's a remote sensing expert. He looks at satellite imagery data and he tries to discover things about the atmosphere and the climate. And the cardiologist said, hey, we have some data about Kawasaki's disease, which is an inflammatory heart disorder. It can be deadly, and it's seasonal. And the idea was that basically there were spores that caused Kawasaki disease that were being long-range transported over the ocean, and dust, aerosol in the atmosphere was actually preventing these things from getting zapped by UV. And one of the things that we want to do is actually see if we could predict whether or not some sort of atmospheric conditions would be indicative of outbreaks of Kawasaki disease. And so working with Nick LaHaye on the left, who's a PhD student of mine at JPL, and Jordan Ott, who's a master's student of mine who I really want to stick around for a PhD, but he has bigger and better plans. So maybe he'll stick around anyway, I hope, if I guilt him into it. We decided that we'd build some deep learning models using deep belief nets, and we could find some interesting stuff. One, we could find that we did actually see some atmospheric trends that were perhaps indicative or predictive of Kawasaki disease updates. And the second thing that we discovered is using some deep learning techniques, computer vision techniques, we could actually take sensors on satellites like Terrasat that had totally different modalities and were picking up all sorts of different data and fuse them together to get a much richer view of what was going on. And again, the only way this is possible is because we were working with a cardiologist and an Earth system scientist and someone at JPL who knew how these platforms actually worked, and that was great. Well, it's funny how things come full circle. The last couple of months I've been working on mining software again, only this time doing something completely different. Rather than actually looking at software as text, we were looking at software as images. So pretend that the computer looks at source code, at software, with the same eyes that we as human beings look at software and source code. What can it learn? And one of the things that we found out was using convolutional neural networks, it can learn a lot. And in fact, this picture on the right is the same as the picture on the left, except it's the computer learning what things are important and predicting whether or not something is Java code. So things like variable declarations and code structuring and curly braces and things like that. So we've just written this up and submitted it for publication, and it would be lovely if that got accepted. But again, you have Abigail Atchison on the right, who's just an absolutely brilliant young undergrad who's already interned at Microsoft and Amazon, and Jordan Ott, who has great deep learning experience, Paul Harnack, who's a software engineer among software engineers. When this kid goes out and gets an industry job, he's going to turn some heads. And then Adrienne Berg, who's working on her master's in computational and data science. That's been really helpful in kind of bringing the team together. So just lots of different backgrounds doing cool stuff like training a computer to know Java code. And the idea behind this is there's so many online tutorials now where you can go and learn Java. We basically wanted to be able to cheat and say, here are all the code examples in the video that were worth looking at. So this is neat. This is neat work. And it's about as cutting edge as you can get from a deep learning perspective using convolutional neural networks. That's sort of the state of the art in machine learning right now. And certainly plenty of data when you're talking about this type of stuff. I mean, we were scraping terabytes and terabytes of video data to be able to do this. So definitely big data. So that sort of takes us back to this sad little scatter plot. And my disappointing first impression about machine learning and data analytics and data mining or pattern recognition and whatever the heck you call it. And the idea that it sounded like a really lousy career to spend my day figuring out the parameters of the line of best fit that went through a cloud of points. Well, it sort of turns out that hindsight's 20/20, and whether or not this is an interesting graph sort of depends on what the domain is. And when I just look at it as a predictor variable and a response variable, it's not very compelling. But what if I said that the x-axis was treatment hours that a kid in the autism spectrum was receiving, and the y-axis was how quickly they achieved their learning objectives? And then I said that that simple line accounted for about 34% of the variance in skill acquisition. So in other words, if you had to turn a knob and that knob would tell you that you could help a kid learn more and help a kid learn less, that knob would basically be how many hours of therapy you'd be getting. And that plot is this plot. And here's a paper that we did that was submitted to behavior modification and had spawned off some different derivative papers that is probably the work that I consider to be the most meaningful and the most important of my entire career to date. And for the most part, it's based on simple linear regression. And the reason why it matters so much is because we have a team of grad students with a database background and a statistics background and a machine learning background combined with experts in psychology and neuroscience and behavior analysis. And we brought all the right people into the room. And then suddenly this problem that seemed sort of boring was all of a sudden something that was really sort of pretty and something that we could do something about. So in terms of big data and the hype surrounding it, really it all gets down to the fact that thanks to the internet, we can get our hands on huge volumes of data sets, many of which are publicly available. We have improved algorithms for dealing with that data. We have improved hardware for dealing with that data, including GPUs. And certainly the cloud makes it possible for folks that don't have the infrastructure right there with them to be able to compete with groups and of scientists that do. And most importantly, we have a way to communicate with all sorts of domain experts around the world, so you always have the right people in the room when you're working on a problem. So to me, that's the real beauty of big data. It's not so much all the hyped words, but it's the fact that if you want to build a computer machine learning algorithm that beats the game of Go, if you want to build a self-driving car, you need a lot of people in the room. They're all going to have very different backgrounds. They're going to have to learn how to talk and collaborate. But when they do, they're going to do really phenomenal work. So getting back to my quote by Richard Feynman, big data is great, but at the end of the day, no problem's too small or too trivial if you can really do something about it. Here's the group that I'm lucky enough to collaborate with every day in my job at Chapman. There are people here that are chemists and biologists and psychologists and computer scientists and sociologists and pharmacists and physicists and Army veterans, first-generation college students, and first-generation Americans. And this is what makes big data fun for me, beyond just the size and the volume. So thank you. That's what I have to say.